In this video, we're going to use Grignard reagents to do reactions with organic compounds, starting with epoxides. So in OCHEM 1, you learned about creating an epoxide from an alkene, and then we added in nucleophiles, and we saw that a nucleophile in base is going to attack the least substituted carbon of an epoxide. In this first example, the epoxide is symmetrical, so we don't really have to worry about that. But the important thing that I wanted you to see already is that this is a nucleophile in basic conditions because this is a strong base. So our Grignard reagent is going to attack the epoxide just like a nucleophile. So that we end up creating a bond to the epoxide. So these two carbons are from the epoxide. And then we've broken open the epoxide so that we have a bond to oxygen, which is negative out here. And then you would have to add in some sort of proton source. So you could do an aqueous acid workup. Sorry, that says plus. And so what we've created is an alcohol that is 2 carbons larger than our original compound. So anytime that we're able to create carbon-carbon bonds is really beneficial in organic synthesis. So this is a really useful reaction. Okay, so now in this one, we have an asymmetric epoxide. So we have to figure out, are we going to prefer, we'll call it carbon A or carbon B? So go ahead and think about it for a second. So the nucleophile is going to want to attack the less substituted carbon because this is essentially an SN2 reaction, right? And that's our rule for SN2 reactions. So you want to be really, really careful about counting your carbons here. So we have 1, 2, 3, 4 carbons in our Grignard reagent. 1, 2, 3, 4. We've now created a bond to the epoxide, and our epoxide has 1, 2, 3 carbons in it. So 1, 2, 3. And then carbon 2 is going to have the oxygen sticking off of it. So you have to be really, really careful here. It's really easy to end up with too few carbons or too many, or to end up putting the oxygen in the wrong place entirely. And then we would want to add in some sort of proton source. So that we can have our alcohol product. So again, the Grignard will attack the least substituted carbon. So then we can also use Grignards to attack carbonyl compounds. This is going to look a lot like those reactions that we saw at the very beginning of this chapter, where we just took a generic nucleophile and attacked a carbonyl. So we have these electrons in the bond between the carbon and the magnesium. And we attack the carbonyl carbon, and we push the electrons up onto the oxygen. So after step 1, we have our benzene. This is the new bond that we just created. Here is our carbonyl carbon. And then the carbonyl carbon should have a methyl, and an oxygen sticking off of it. So methyl, methyl, oxygen, which is negative. And then we add in aqueous acid so that we can protonate it. So our final product would be an alcohol. So this is the type of problem where counting the carbons in your starting reagents and then comparing that to the carbons in the product that you've drawn can be really useful. So there are 6 carbons here and 3 here. which means that my product should have 9 carbons. So I have 6 in my benzene ring. I know that that's good. 7, 8, 9. So I at least know that I have the right number of carbons, which is definitely the most common mistake. So we're going to do a couple practice problems. At the beginning of each practice problem, just take a second to pause, and then I'll continue on with the solution. But you should definitely be trying these reactions on your own before listening to the answer. Okay, so in the first step here, we are adding in magnesium metal to an alkyl halide in THF, which is an ether. You may not recall the structure of THF, but it's a cyclic ether tetrahydrofuran. And it's just your solvent, so it's not going to be really involved here. And we're going to insert the magnesium between the carbon and the bromine to create a Grignard reagent. So that's the purpose of step 1. Now in step 2, we're adding in cyclohexanone. So the Grignard reagent is going to be attacking our carbonyl carbon. So let's go ahead and just draw out our product, but we're going to keep in mind that we're not going to lose this oxygen. It's going to turn into a singly bonded oxygen with a negative charge. And then we have to add on 1, 2, 3, 4 carbons. So 1, 2, 3, 4. And then in the last step, this is a protonation step. We're going to protonate our alcohol, and that gives us our final product. Okay, go ahead and pause. Give yourself a second to try this one. Okay, so in this one, the Grignard reagent is already formed for us. So we're going to take our Grignard. The electrons between the carbon and the magnesium are our nucleophile, and we're attacking the carbonyl carbon. No, that is not what it looked like I drew. And we're going to push the electrons up onto the oxygen. So I'm going to draw our benzene. This is the bond that we've just created, and it's going to be attached to the carbonyl carbon, which has 1, 2, 3 other carbons coming off of it, an oxygen and a hydrogen. So 1, 2, 3. We have a singly bonded oxygen and a hydrogen that we don't necessarily need to draw. This will be a good point to go ahead and count your carbons and your starting materials in your product. So we have 6 over here. We have 4 here. We should have 10 in our structure. So we have 6 in the benzene ring, 7, 8, 9, 10. So far, so good. And then the last step is to protonate. And I'm not going to draw the aldehyde hydrogen in again because it is implicit. Okay, this next problem is a challenge problem. We have not done a reaction with esters yet, but I want you to go ahead and just think about it for a second and note that there is an excess here. So go ahead and pause if you haven't already. Okay, so in this reaction, the Grignard is going to attack the ester, which pushes the electrons up onto the oxygen. So we have this O-, we have our ethoxy group, and then we also have the 3 carbons that we just added from the Grignard. Now, this looks a little different than what we've already seen. So far, we've only done reactions with aldehydes and ketones. Now we have this ethoxy group here. for a second, I want you to think about how common it is to have two oxygens attached by single bonds to the same carbon. You don't see that very often. And if we were to protonate this, it would form a compound that's called a hemiacetal. And later in the semester, we'll learn that hemiacetals are not particularly stable. And so instead of protonating, we do something else. We reform the carbonyl and we kick out the ethoxy group. So now we have a ketone, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, and the ethoxy group is out here in the ether, just kind of gone. But we have an excess of Grignard. If there is excess Grignard in the reaction, does a Grignard react with a ketone? Is this something that we've seen before? Absolutely it is. So the Grignard attacks again, and we push the electrons up onto the oxygen. And then we can protonate this. So after step 2, when we've added in ethanol, we end up with a tertiary alcohol. So now we're going to wrap up all this information into 2 easy to flip through slides. So if we react a Grignard with formaldehyde, I'm just going to draw out a generic Grignard. And remember, formaldehyde is the smallest formaldehyde. It's a 1-carbon aldehyde. If the Grignard attacks this and then we protonate it, what is this going to look like? So our first set of conditions would involve ether for the Grignard, followed by an aqueous acid workup. So what we would end up with is our R group attached to a CH2 group from the formaldehyde, and then an alcohol. So what you essentially get is an alcohol, a primary alcohol, that is 1 carbon longer than your original R chain. If you react a Grignard plus any other aldehyde, so we're going to draw a general aldehyde, you end up with a secondary alcohol. So imagine that R group attacking the carbonyl carbon. And this is what we would end up with. The aldehyde hydrogen would still technically be there, we just don't need to draw it out. If we react a Grignard with a ketone, we end up with a tertiary alcohol that has a whole bunch of potentially different R groups on it. And then lastly, with our ester, we have to have an excess of the Grignard, we also end up with a tertiary alcohol. But notice that we end up with 2 R groups from the Grignard, and then the R group from the carbonyl side of the ester. Whereas in the previous one, the Grignard R group appears once, the R prime group appears, and so does the other R group. Oops. So 2 different ways to make a tertiary alcohol, but depending on the structure of your tertiary alcohol, that can help you decide whether a ketone or an ester might be a better starting material, or maybe it doesn't matter at all. You might be able to do your synthesis either way. So this brings us to a synthesis problem. I'm actually not going to go through this in the slideshow. I'd like you to think about it and come to our next class period with this synthesis worked out. And I'm going to go ahead and tell you there are 3 different ways to do this synthesis. So if you can come up with all 3, you're in an even better spot. So synthesize the compound below using a Grignard reagent, and you may use an excess of the Grignard if you would like to, and a carbonyl compound. Notice that the directions do not tell you which carbon piece has to come from the Grignard and which carbon piece has to come from the carbonyl compound. That's actually what allows this to be done in 3 different ways, is that you can switch that up. So the last thing that I want to talk about with Grignards is that there are some pretty serious restrictions on Grignards. So you cannot form a Grignard, meaning you have an alkyl halide and you add in magnesium metal. You cannot form it in the presence of any acidic hydrogen atoms. So these cannot be present on the substrate, like as part of another functional group, and they cannot be part of the solvent. And the reason why is once you form your Grignard, you're going to end up immediately deprotonating these and neutralizing your Grignard. Grignards also cannot be prepared from a compound containing an aldehyde, a ketone, an ester, an amide, a nitro group, which is NO2, a nitrile, or an epoxide, because it's just going to end up reacting with it. So it could do a nucleophilic or an acid-base reaction. And again, the substrate must not have acidic protons present, and neither can the solvent.